Hello, everyone. I'm Rudy Schubert from the IEEE SA, where I am the director of our energy practice. And I'd like to welcome you to today's webinar on IEEE Standard 2800, which is interconnection standard for large-scale solar, wind, and energy storage. I'd like to thank our partner organizations that help get the word out and we're engaged in the development of this standard. And we know this is a very exciting standard that people are very enthused to know more about, because we had over 2,000 registrations for today's webinar, which I think may be an all-time record. So the 2800 was just released on Earth Day, actually, on April 22nd. And I'll tell you about a few other things that are going on in parallel to its release as we go on. First, a few housekeeping items before we get into it. Everyone who is on the line today is going to be muted automatically. It's a one-way broadcast, but you do have the ability to use the Q&A section to ask questions throughout the webinar. There is also a chat feature, and that should only be used if you're having technical issues with the webinar itself. So any questions you have, put it in the Q&A. We will do our best to get to as many questions as we can, but given the large size of the audience, it may be a bit challenging. So we will be looking through those and trying to answer as best we can some of the key ones that come up. All right, that's sort of a duplicate. All right, just another quick disclaimer before we get going. The views presented in this presentation are the personal views of the individuals presenting it and should not be considered the official position of the IEEE Standards Association or any of its committees, and shall not be considered to be nor be relied upon as a formal position of IEEE in accordance with the IEEE SA Standards Board bylaws. And then there are a few other items that you can see down there that all have to do with some of the things that you have in the bylaws. And I won't go through all of those in the interest of time, but we do want to make sure that everyone is aware of this, that our presentation is really to educate people on the new 2800 standard, and it's not to be construed as lobbying or anything where we're driving the adoption of the standard itself. It's really just for education, so people get interested in it and are able to use it as they see fit. So I did want to bring up that in addition to today's webinar, there are two more webinars going on this next couple of days. Tomorrow, there is a joint NERC, NATF, NEGF, EPRI webinar that is some of the same material, but it's really geared towards transmission planners. And you'll see that there is a link on the page there. It'll come up later in the slide presentation as well, where you can sign up, and there's no registration required. You can just join. And then there will be another webinar in the near future coming from SCIA ACP, and that one's going to be geared more towards OEMs and developers. So you're able to actually connect to those links. This whole presentation can be found in the resource section that you should be able to see on your side screen. There's a box with resources, so it has the link to the presentation itself, as well as some other useful resources. And speaking of useful resources, a couple things we wanted to point out. There is a blog article that is talking a bit about 2800. You can find that on the IEEE Beyond Standards website. Again, the link is there towards the bottom left section. This information about the standard itself, how to order it, you can see in that top left section. There's another link, and that takes you to information about the working group and the ability to get the standard. And then another thing that was kind of interesting on the right side, Jens may speak a bit more about this as we go on, but IRENA actually recently released a document on grid codes for renewable power systems. And it did feature a line in there that you see highlighted that IEEE 2800 will be a regional code for North America, with the main area of applicability being the United States, but is designed to go beyond this scope and clearly be recommended as an option for international standardized technical requirements for generators. So we were glad to see that they included that in there, which gives further credence to the importance of this particular standard. And then you'll see another link to ESIG also has a document talking about 2800. So a lot of really good resources that will help you learn more about it in addition to this webinar. All right, so how we're going to do this webinar today, that first bullet, the welcome, that's kind of what I just did. Most of the presentation today is going to come from Jens Bomer, who was the working group chair from 2800, but we also have on the line Jason McDowell from IEEE, Raja Ayanar from PCERC, and Yulu Liu from Current, as well as Stephen Solis from ERCOT is on, and a few other key working group members who may get introduced later as well, who are helping out, trying to sift through the questions as we go on. And so Manish Patel is on. He'll be helping with the questions. I think I covered everyone else. And so Jens will go through the more detailed presentation. We'll have some comments from a utility perspective from Stephen, and then hopefully we'll have enough time for a good, robust Q&A towards the end of the session. So with that, I am going to turn the microphone over to Jens. And Jens, are you on?
Yes, I am on. And I would like to welcome our joint hosting organizations. Thank you, Rudy, for your introduction. And we'll go through a couple of introduction words by Jason McDowell from IEEE, then Raja Ayana from PCERC, and then Yilu Liu from Current. So Jason, if you may want to take the stage for a minute or two.
Excellent. Thank you, Jens. Thank you, everyone. My name is Jason McDowell. I'm the chair of IEEE's Reliability Working Group and senior director at GE Energy Consulting. And on behalf of the Energy Systems Integration Group, I'd like to welcome everyone to this webinar. Thank you all for participating. And I think we're going to learn a lot today about the great work that went into developing this monumental standard for the industry. I'd also like to congratulate the full IEEE 2800 drafting team and its leadership for highly commendable work to advance the industry and define capability requirements for inverter-based resources. IEEE is an organization focused on system integration and dedicated to working with our membership and industry stakeholders, including standardizing bodies like IEEE, as well as regulators, system operators, equipment owners, OEMs, and many others to uphold grid reliability, resiliency, planning, and operations as we progress through the energy transformation. IEEE 2800 is a critically important and notable step forward on this journey to unlocking the full potential of inverter-based resources on the grid. We're greatly looking forward to working with all industry stakeholders on identifying the next stages of deployment and how IEEE 2800 requirements can fit in many of the industry stakeholders today. So thank you again, and Jens, I'll hand it back to you.
Thank you so much, Jason, and welcome all those IEEE folks out there. I'll hand it over to Raja from PCERC.
Thanks, Jens. I'm Raja Ayanar from the Arizona State University, representing PCERC. PCERC is excited to co-sponsor this webinar. PCERC stands for Power Systems Engineering Research Center. It is a leading research consortium of 13 universities and about 40 industries across the country. Arizona State University is the lead institute. The center started in 1996 as an NSF Industry University Cooperative Research Center, and all our research under three main stems: power systems, T&D technologies, and power markets. They're all primarily industry-driven, solving specific industry challenges with creative research. Many of our researchers and industry partners, they have strong expertise and really high stakes in inverter-based resources and the integration at the bulk power system. Our current research in this area range from protection of IBR-dominated power systems to advanced modeling to design of power systems with 100% IBR penetration with the emerging grid-forming inverters. So there's a very strong interest in the PCERC community about the IEEE 2800 standard, and also including how to incorporate that into our graduate curriculum. So very excited and honored to welcome such a large audience. And back to you.
Thank you so much, Raja, and welcome all the PCERC folks out there. I'll hand it over to Yilu from Current.
Thank you, Jens. I'm Yilu Liu, representing Current. And actually, Current is a NSF DOE co-funded engineering research with a total of a government funding around 40 million. We have started our first year milestone into after graduation, so this will give us opportunity to focus on industry. Our center has around 35 industry members representing many different areas, ISOs, vendors, utilities, and software manufacturers. We have around 150 graduate students, 4 schools coming from 4 schools that are having around probably 30 faculty members. We have 2 signature that I like to product related to power grid. I like to mention, highlight. We have a joint, very much tight research between power electronics, power system faculty, and we have the world first hardware test bed, which is made of all inverters, and it's ready to do all kinds of testing, real-time simulations. We also operate the large grid monitoring system that's covering North America and also major grid of the world. Yeah. So IEEE 2800 is a milestone document. This is a historical moment for the release of such a document. It will be followed by all different entities to give us as a guide for us to produce the next generation power grid. This is extremely important document. I hope all the audience will enjoy as much as I do learning about it. Thank you.
Thank you so much, Yilu, and welcome to all those Current members out there. All right, we have quite a bit of material to cover. As a matter of fact, you should be able to download the slides already now. And you will see that we will have way too many slides to go through in detail, but we wanted to get the details into your hands for your review. So what I'll do is I'll focus on the scope and the purpose and how 2800 came into being and what it is all about, and then give you a high-level review of what the entirety of requirements is inside of the standard, and then blaze through the specific selected requirements for your information. And I'll finish with a few words on potential adoption of 2800 in North America before I'll hand it over to one of the ISOs, Stephen Solis, who has actually already started adopting the standard or going through a process trying to do so. So just the same disclaimer as Rudy mentioned, but I would like to acknowledge the support from the Department of Energy of several folks who contributed to the standard's development. Without their support, the standard would not have been developed in such a short time. 2 years drafting, 1 year balloting is almost a record for a IEEE standard. So thank you very, very much for that, and also additional support for related projects. Rudy already mentioned this IRENA report. IRENA is the International Renewable Energy Agency. They are located in Abu Dhabi, and I would say coincidentally, they issued a report pretty much a day or so before IEEE 2800 was published on Friday, April 22nd, which happened to be her Earth Day. And they published a report that really emphasized the fact that power system transformation towards the decentralization, digitalization, and electrification calls for evolving what they call grid codes. And some people could consider IEEE 2800 as one of those grid codes. Now, grid codes are usually more than just connection codes. Europe has, for example, a very dedicated framework of connection codes, operation codes, and market codes. And IEEE 2800 can be a cornerstone in this context for North America. The IRENA report found that IBRs, which stands for inverter-based resources, impact the way power systems are operated. They clarify that grid codes like 2800 are meant to build trust between different actors during the interconnection process. And it's even better to have an imperfect standard than no standard at all. And those standards should be technology neutral to the extent possible and should also be set up such that they can evolve with the system needs. The standard should enable innovations. That is one reason why IEEE 2800 was written as a performance standard and not a design standard. So it allows for different ways of meeting the performance requirements specified. Now, what's really key is that whatever is written on paper also needs to be verified and tested to ensure compliance. Without the compliance, a standard like 2800 is not fully able to unfold its value. Yet it can already level set expectations for new inverter-based resources when they interconnect to the grid. And international standardization is also important, and you will find that IEEE 2800 has leveraged a lot of international experience. I still remember a couple of calls with folks from Europe and Australia, from which we were able to learn during the drafting of IEEE 2800. So in a nutshell, this standard is a cornerstone in the transforming power system. And at this point, it is tailored to the North American context and yet could also be applicable elsewhere. Now, what is really the driver behind the development of such standards? The driver is the high pace of interconnections from inverter-based resources like wind, solar, and storage. And if we project this into the future, and we have some of these generation duration curves here shown from the NREL solar future studies on the right, we can see that at least in some hours of the year, each one of those large interconnections will experience very high penetrations of inverter-based resources that are beyond 75%. And some of them go even up in a few decades to 100%. So since we are connecting some of the plants that will be operating in those future scenarios as they remain in the system typically for about 20 years or so, we are connecting those today. We also need to make the best informed choices about capabilities of these plants today and cannot wait, deferring those decisions into the future. So what IEEE 2800 addresses are the minimum technical requirements that are deemed needed for inverter-based resources that are still operating in 20 years from today. Well, how does the landscape look like today? Today, it is probably fair to say that in general, there is an insufficient specification of interconnection requirements across North America. The requirements are fairly diverse and also different, which makes it more difficult for developers to tailor their interconnection and design to specific requirements of certain regions. Also, we need to recognize that inverter-based resources perform differently from synchronous generator. And that can mean that they have actually higher capability, for example, to ride through faults longer and of more severity. But some capabilities may be lower. So the differences need to be accounted for when we draft specifications. And last not least, some of the requirements that exist today may not be fully balanced. Some stakeholders may perceive them as too stringent, whereas others would consider them not taking full advantage of the existing and new capabilities that wind, solar, and storage provide. So that's the starting point, which really was at the beginning of IEEE Standard 2800. Now, in addition to that, NERC has identified recurring reliability issues with inverter-based generation that include unexpected tripping, momentary cessation of active power, and power oscillations. Some of those can be potentially attributed to misapplication of another IEEE standard, namely IEEE 1547, that was written for inverter-based resources and synchronous generators connected to the distribution system. Now, those requirements are not necessarily applicable to transmission-connected resources. And that was one of the gaps that IEEE 2800 is trying to fill. Now, the analysis of FERC also found opportunities for more standardization of the performance. They did issue several reliability guidelines, but more recent events showed that those recommendations from those guidelines have not been followed by developers across the country, and therefore having a common standard can potentially help improve the situation. More specifically, NERC identified a couple of causes for solar PV reduction. Those included the loss of synchronism of the phase lock loop, inverter under or over voltage tripping, inverter under or over frequency tripping, slow active power recovery after the ride-through operation, and even momentary cessation during the ride-through operation, but also some inverter overcurrent tripping and other potential causes. Now, NERC has strongly recommended to consider significant updates and improvements to the FERC Large Generator Interconnection Agreement, the pro forma agreement, and also recommended improvements to NERC reliability standards to address some of those systemic issues. Let us try to contextualize where IEEE 2800 and also its complementary recommended practice, which will be IEEE 2800.2, might fit into the North American interconnection process. And this slide shows not only the process as it is laid out in the pro forma FERC LGIP, but it also highlights in red some of the big gaps that are potentially included in this process with regard to power system reliability. So the first step is the interconnection request. And as we said before, the requirements for technical interconnection might be insufficient. And that is really the key place where IEEE 2800 2022 can potentially level set and create more harmonization and clear expectations for all the stakeholders involved, including developers of solar, wind, and storage plans, as well as the grid planners. Now, step 2, which is the feasibility study, might have some deficiencies in terms of screening. And many of the ISO RTOs in some of the regions have already addressed and started revising their processes. But ultimately, it comes down also to modeling of these resources. Now, one of the challenges with regard to resource models is that in the past, there was no clear expectation for performance. So adding 2800 as expected performance requirements can also reduce the uncertainty with regard to performance of these resources, and that might increase the opportunity to use models that represent those resources more adequately. That is important for step 3, the system impact study. So often impact studies are not fully based on reasonable modeling assumptions. or model parameters. With 2800, in those cases where there is no additional information that might be site-specific to a given plant available, at least some of the generic parameters and default values shown in the standard could potentially be used to go through the first round of the impact study. Now, shall they be updated with more sophisticated models and parameters? Of course, but only once the specific equipment is selected by the developer can those models be updated. And in the facility study, which is in step 4, this study has traditionally focused on cost estimation for transmission grid updates. Now, what has not been done in the past is a common assessment of IBR plant level conformity with any of the technical requirements, which may include a more detailed plant design review in order to understand to what extent these requirements are met. So this is where the new recommended practice that just started to be developed under 2800.2 can potentially fill that gap, which then leads to the construction of the plant where as-built plant level evaluation may verify that the plant is actually designed, actually built as designed. And then 2800.2 might also specify interconnection commissioning procedures as well as post-commissioning requirements. So this is just to contextualize where 2800 fits into some of these processes. What's the scope of 2800? It establishes the required capability and performance requirements for resources connected to transmission and sub-transmission systems. And that includes voltage and frequency right through, active power control, and a whole bunch of other things that are important for system reliability. It does apply to wind, solar, and storage. That includes type 3 wind turbines, but it also applies to inverter-based resources connected via voltage source converter tie lines to the AC grid. So the summary of what 2800 really provides is a set of harmonized interconnection requirements. It is a consensus-based document that was developed by more than 175 working group members, from which I know many of you are here on today's webcast. And I think the whole industry owes you so much for your dedication, your time, and your diligence developing the initial ballot draft of 2800. But then another set of gratitude goes out to around 466 Standards Association balloters who took the time to review diligently the 172-page long document, formed their opinion, submitted 2,000 comments, and finally made up their mind whether to vote with approve, disapprove, or abstention. And remarkably, the final document that you see published today has received an approval rate of more than 94% among those balloters that voted. Just to place 2800 here in the American reliability standards context, it's really about the performance. It covers transmission and sub-transmission, whereas IEEE 1547 2018, as well as the amendment of that standard from 2020, is addressing the distribution connected resources. And as any IEEE standard that is voluntary, it only becomes mandatory if the appropriate authorities would adopt this standard. Standards are really at the top of the IEEE document pyramid shown here because they specify shall requirements, whereas recommended practices such as 2800.2 and guides are specifying should or may language. What can you expect from 2800.22? It provides value due to the widely accepted and unified technical requirements. it can potentially simplify and speed up technical interconnection negotiations and processes. And you may remember the process slide. Now, even with more reliability checks during the process, having a unified set of technical requirements may actually end up expediting those processes, which we all know are heavily clogged up here in the North American interconnection curve. It also provides flexibility for developers and OEMs because it is not a design standard. It does specify performance and functional capabilities, but it remains silent on whether or not to utilize those. It specifies functional default settings and the ranges of available settings that then determine capability. And it even lays out some of the performance monitoring and model validation. Now, it also lays out a framework for tests, planned evaluations, and other verification means for each of the requirements in a many-page-long table, but it does not specify the procedures that actually underlay such verifications. There are a couple of things that you cannot expect from IEEE 2800. It does not provide exhaustive requirements for any evolving IBR technology solutions. So for example, we talked about grid forming inverter controls in the IEEE 2800 working group and balloting process. And even though the standard was written such that we hope it does not create any barriers for application of grid forming inverters, it was really originated from a grid following inverter-based resource control perspective. So if you come across any technical barriers, any technical specifications that might contradict grid forming IBR technology, let us know, and we'll look into this as we all learn together how to improve these standards in the next revision. Another area was synchronous condensers, which might be used inside of an IBR plant to provide stability, especially for weak grid conditions. And even though 2800 considers synchronous condensers, if they are used inside of the plant as what we call supplemental IBR devices, it does allow for some exceptions and encourages the grid planner to carefully study using validated models the interaction of these synchronous condensers and whether the plant, including the condenser, would still comply with IEEE 2800 performance requirements. The standard also does not define an interconnection process. This is really up to the transmission owner and their stakeholders and regulators, but it can be part of such a process as laid out on the process slide before. And last not least, it does not specify the procedures to verify that IBRs actually comply with the requirements of the standard. Those procedures are currently being developed in 2800.2, and you can follow the links and get signed up to engage in that drafting process if you are not already engaged today. A little word about capability versus utilization. Capability is really the ability to perform, or you can translate it into the decision what type of technology you purchase. Looking at a comparison here with cars and street rules, the capability is the decision whether you go for a horse carrier, a medium-sized vehicle, or like a race car. Whereas the utilization of that capability is really the decision about whether or not to deliver the performance that is specified. So in other words, utilization of the capability relates to the speed limits that the race car, even though it might be capable of driving fast, would still have to abide based on the rules and the agreements that in case of inverter-based generation and storage, the transmission planner and the plant operator would agree on. So capabilities can include frequency response and write-through, whereas utilization then really depends, is determined on the chosen parameter configurations for the deadbands, the droop, the response times, or even the decision to operate a plant with headroom. And one more comment on this, 2800 is all about capability and is not specifying mandatory utilization of any of that capability. Also, it's important to understand where 2800 applies. This is a fairly complicated chart of inverter-based plants with collector buses, inverter units, step-up transformers, and then an intertie line connecting to the transmission grid. And you will see that the default reference point of applicability, RPA, is really where the point of measurement is, where the plant connects to the tie line. But many transmission planners may decide to adopt 2800 by moving the RPA to the point of interconnection where the tie line actually connects to the transmission system. The minimum requirement specified in the standard is to meet the requirements at the POM, but it might be applied at the POI. And for voltage source converter connected resources that are here in this isolated part of the, for example, an offshore wind park, the standard does not apply to any of these isolated IBRs. It only applies to the point of measurement of this combined HVDC VSC with IBR facility, where it connects either to the tie line or the AC transmission grid at the POI. This is the slide that really shows us what's all included in IEEE 2800. And if you ask some of the folks that were involved, especially those that work for transmission planners and grid companies, they kind of start telling you that this standard gives them more than they ever imagined they could need, because for the first time, they went through a very deliberate conversation and learning process together with the OEMs and the developers to really understand what the new inverter-based resource technologies are capable of providing. So this is a pretty impressive set. And yet, on the other hand, when you talk to developers and OEMs, they're also excited about this because for the first time, they have a clear guidance about what the grid planners would actually like to see. In the past, they sometimes couldn't really get clarity on what the grid side wanted them to provide. So this trust that has been built has led to an impressive set of capability requirements ranging from frequency response over reactive power voltage control, over power quality, over write-through, coordination of protection, and also modeling and validation measurements, all the way to at least the framework of test and verification requirements. Now, you see this red line shows the technical minimum bar, and you see that the bar is pretty high now. There are just a few things that are not included in the technical minimum requirements of 2800. And those include, for example, harmonic voltage limitations. Those are not specified in the standard, but the standard does recommend the transmission system planner specify those harmonic voltage limitations. Also, the standard does not specify the processes or the criteria for model validation, but it does require validated model. And for fast frequency response, the requirement is only mandatory for under frequency conditions, whereas for over frequency conditions, it is optional as of this version of the standard. And for reactive power, the standard specifies that all inverter-based generation shall have the capability to even provide reactive power at zero active power output. So you could say that, for example, a solar PV plant would have to be capable of providing reactive power even at night. Now, does that mean that it has to provide that reactive power at night? No, it does not, because as you remember, the utilization of these capabilities is outside the purview of 2800. So let's look at some of these things a tiny bit in detail. We have to now abide with the timing here. We have about maybe 20 minutes left on the presentation. So we'll blitz through some of the next slides and then conclude with some of the potential adoption comments. You may see that in some slides we use simulations, and some of those simulations were generated with the lumped model and infinite bus representation as shown here. So minimum reactive power capability requirements. The minimum requirement is to have capability for 0.95 power factor, but type 3 wind turbine based IBRs have a slightly reduced capability requirement compared to the other plants that shall have the capability to provide full reactive power output even at zero active power output. And now for AC connected offshore plants, there's also an exception allowed, but it shall not require the capability, a capability that is less than what is shown here for wind turbine generator type 3. And the reference point of applicability is the point of measurement. The same holds for storage IBRs that would be capable of consuming active power, so to say, in the other side of the plane. And that reference point is called this IBR continuous absorption rating. And also for these plants, it is required to have a rectangular capability with 0.9 power factor at the point of measurement. Even for different voltage values in the continuous operation region during normal conditions, the standard does require full reactive power capability between those specified points V2 and V3, but it does allow for some reduced capabilities at those corner points. The voltage and reactive power control modes include voltage control mode at the RPA, power factor control mode, and reactive power set point control mode. The voltage control is a closed loop automatic voltage control to regulate the voltage. It is capable of reactive power droop to ensure a stable and coordinated response. And you see on the table on the right side that the standard specifies some of the performance requirements, such as a reaction time of less than 200 milliseconds for this type of dynamic reactive power provision, and a maximum step response time that is specified by the transmission operator during the adoption process, but typically ranges between 1 second and 30 seconds. In any case, the standard specifies that the stability of this control shall have a damping ratio of 0.3 or better. So just to give you an example here based on a simulation, it is up to the transmission planner to study their system and decide whether they like to have a response that may be as fast as 1 second rise time or as slow as a 30-second rise time or anything in between. Whatever they choose, they shall make sure that the control configuration leads to a damping ratio of 0.3 or better, which corresponds to the orange line in this figure, and anything that oscillates less than this orange line. So for example, the green or the red line. For frequency disturbance and write-through capability, the 2800 requirements are fairly well aligned with what folks may already know from IEEE 1547 2018, a 5-minute write-through capability around the nominal frequency with requirements to maintain synchronism, to meet the active power requirements of the primary and or the fast frequency response, and also to maintain the reactive power output at least within the volts per hertz limits. There's one exception that within the volts per hertz limits of IVR units, transformers, and supplemental IVR devices. For example, if the frequency is low and the voltage is high, the volt per hertz might exceed the capability of the equipment, and in that case, there might be exceptions to the write-through requirements. The primary frequency response capability is specified similar to IEEE 1547. Now, one important concept to highlight is the so-called IVR short-term rating. That might be a specified and agreed upon megawatt value between the grid planner and the developer that exceeds the continuous rating of the plant and could therefore potentially be used in order to provide additional active power, at least for short-term time periods. And the standard also includes these ranges and default value for the deadbands and the droop factor. It also includes a specification of the time response with ranges of available settings and default parameters. The stable and damped response shall take precedence over the rise time and settling time. So the standard does not let grid planners not make informed decisions about the configuration, but it encourages them to really study their system and require from those plans what the system needs at this specific connection point, for example. Fast frequency response is a capability that is also sometimes known as inertial response. It's currently only specified for under frequency conditions, and it really aims at arresting the frequency decline when, for example, a large generator is lost, or even during system split conditions. There are a couple of specifications, but the key one is that the fast frequency response shall have a response time no greater than 1 second. And this function is still an evolving function, so the requirements are fairly high level and not as specific in this version of the standard. However, for wind-based IVR plants, the fast frequency response requirements have been carved out to be a little bit more specific based on OEM feedback. Now, why is this even relevant? It is relevant because in a high inverter-based penetration power system, the active power response from these inverter-based resources can really impact the stability of the grid. This is a simulation that EPRI conducted a while back and looks at a test system with 2 large 200 megawatt inverter-based resources. And this study looked into the ramp rate capability, which also includes the capability of the resource that is behind the inverter coupling to the grid. In this graph, you see just a slight difference of the active power command in red and orange for 2 different ramp rate capabilities, one for 1 per unit per second and the other one for 10 per unit per second. So you see the orange line has a steeper slope because it has a higher ramp rate capability and set point. Now, the resource follows slower than the set point, but still the resource with the higher capability has a faster response. both of these responses actually meet 2800 as a standard requirement. Now, when you then operate this system, in some cases even as a 100% inverter-based system, which is created here at 2 seconds, then depending on the ramp rate capability of the source behind the resource, the system either remains stable, as shown in the traces green and blue for ramp rate capabilities of 5 or 10 per unit per second, or it might lose stability, as shown in the 1 per unit trace, which is indicated in orange. So what you can see from this is that fast injection of current in a low inertial system becomes very important, even though in a strong network, the response almost looks very similar to each other. So knowing that the ramp rate capability of the source behind the inverter can make a difference, and knowing that some inverter-based resources may have ramp rate capability limitations, this is another study that looks at what system response you may see depending on how many plants are participating in fast frequency response in this case. And what you see is that if ramp rates are limited, you can still operate the system in a stable manner if you have more of the resources actually providing that response. So what that means and shows is that the more resources you can build up with capabilities early on, the more resources can later, at a high penetration inverter-based system, provide and deploy that response, which then reduces the burden for each one of the resources. And that is one of the key ideas of 2800, introducing a mandatory requirement for fast frequency response early on, so that once we reach those penetration levels at some hours in the year, in maybe 5, 10, or 15 years, we have enough capability built in the assets to then still operate the system. This brings us to the bigger set of requirements, and those are the voltage ride-through requirements. The standard specifies different requirements for wind plants and for solar plants. They are way more extensive than the NERC PRC 24 requirements, and they are true ride-through capability requirements and go far beyond just relay trip setting requirements. There is some carve-out for what we call permissive operation below 10%, which allows momentary cessation, but does not require momentary cessation. Whereas in the mandatory operation region, no momentary cessation is allowed. We'll skip the understanding of the capability curves, which you can read in Annex G, I believe, the standard. And there are a couple of carve-outs for voltage ride-through depending on the unbalances. And also, with regard to the post-disturbance power recovery, for those voltage events where the voltage at the RPA falls below 50% of nominal, the standard allows up to 10% of the total capacity of the plant not to ride through. For example, if individual wind turbines would trip within a park. During the ride-through, there are also requirements to inject current, and those are specified with response time and setting bands. And the current injection shall be voltage dependent. 2800 does not necessarily specify that it be a proportional reactive current injection, as we have, for example, seen in previous versions of the grid codes in Germany, but it does require a active or reactive current priority setting that can determine to which current the inverter gives priority during the event. And it also requires, just as some of the other leading grid codes around the world, negative sequence reactive current injection during the fault period. Here are a couple of illustrations. So when the fault right through occurs, then you see that the voltages in this example drop to 50% at the POM. The RMS voltage is also dropping to 50%, therefore. And based on the standards requirements, the IBR unit is then required to reduce the active current prior to the fault in favor of increasing a reactive current during the fault, and the phase shift happens very quickly here in the first few cycles. And this is also illustrated as RMS currents, fundamental frequency currents, I mean, here in the next figure. Now, if you look at the negative sequence current injection, some of the simulations here indicate a little bit more details, and that include that you can enable the negative sequence current injection. If we zoom in to the fault period, you see that the resource increases the negative sequence current injection, which then also, compared to when this function is disabled, the negative sequence voltage is actually supported, which means that there's less unbalance in the system. And the negative sequence current is something that grid protection engineers are looking for, since they may need negative sequence current in order to detect faults using distance protection where no differential protection is available. And then there is a requirement for transient overvoltage right-through, which is specific to 2800 and, for example, currently not yet included in 1547, although with the new PAR of 1547, that might be considered in a future revision. And this addresses some of the reliability issues identified by NERC in the analysis that we laid out before. This brings us to the last set of slides here. There are a couple of other requirements which I'll just mention quickly. Consecutive voltage right-through, phase angle jump right-through, rate of change of frequency right-through, and restore active power output after voltage disturbance. Voltage fluctuations in terms of power quality, harmonic distortions, and overvoltage contributions are specified. And as laid out before, the voltage harmonic limits are not specified, but the standard recommends the transmission owner to specify those, in addition to the limits for current harmonics that are specified in the standard. But if the plant owner is able to show that they can meet the expected voltage harmonic limits, for example, by using active filtering or active control from the IBR, then the transmission owner may waive the current harmonic limit requirements specified in the standard. Protection is not required, but there's a clear expectation that it will be coordinated with the right-through requirements. And modeling data is required, including verified models. Those can be used to verify some of the requirements that are otherwise not verifiable by tests in the field. And the standard also requires the collection of post-commissioning performance data for monitoring and event analysis, as well as for model validation. This is a test and verification framework laid out in the standard. We will skip this for today, but get engaged in IEEE 2800.2 if you want to learn more about it or share your vision for how this can be fleshed out. And this brings us to the adoption of 2800, which really could start with the gap analysis of existing transmission planner interconnection requirements relative to the mandatory requirements specified in the standard. Now, what's important is to understand that we do not have to wait for 2800.2, which is that recommended practice for test and verification procedures, to be published or even adopted before regions can start adopting 2800. As I laid out on the interconnection process slide, even having a level set and clear understanding of what the performance expectations shall be based on the new standard can go a long way in the connection process and expedite parts of that process without necessarily going into the details of test and verification. It's important to consider enforcement dates, including grandfathering or giving flexibility for inverter-based plants being built at the time of adoption. So that's something that regions will have to carefully discuss and evaluate with their stakeholders. And also whether to adopt the standard in full, simply by a reference, or maybe cherry pick certain requirements and clause by clause, and certainly also consider that 2800 only specifies technical minimum requirements, and regions may choose to set additional requirements, from which probably one of the most likely additional requirement is to move the reference point of applicability from the POM to the POI if justified. I mentioned the 2800.2 process, which is really based on this table that is included in 2800 for the verification steps. And 2800 will develop the details for each of those steps throughout the individual standard process, which is common to standards like 2800, 1547, and 1547.2. So each one of you can get involved with your expertise. Looking at the timeline, we have now successfully published the standard. And I should really say a big thank you also to the IEEE Standards Association, who provides us with the framework to draft, vote, and then publish a major document like 2800, which is really unique throughout the world. The 2800 project is ongoing. There's another 2800.1 project, which is an entity project that is currently on hold. And related activities include NERC guidelines, as well as the ramping up adoption of the standard. So in summary and conclusion, IEEE 2800 harmonizes minimum interconnection requirements for large solar, wind, and storage, including those that are connected, for example, offshore behind VSC HVDC lines. It is expected by many stakeholders to mitigate most of the reliability issues that were identified by the NERC reports and guidelines. Now, as a voluntary IEEE standard, it does require adoption by the appropriate authority before it becomes mandatory. That adoption can commence even before 2800.2 is completed and published. The conformance procedures are currently being drafted in 2800.2, and we would highly encourage everyone, especially everyone who was not involved in the drafting and balloting of IEEE 2800 itself, to join that process. We would love to see even more wind solar storage plant developers engaged in this important 2800.2 project. So you can follow the links and contact Andy Hoke and Manish Patel if you want to go join the 2800.2 working group. And if you have questions about 2800 working group, you can contact myself and Manish Patel or visit those websites. We hope you will be able to study the standard in detail. All the working group members have or will receive a complimentary copy of the standard, and everyone else can obtain the standard here from IEEE. And with that, I would like to thank everyone for your attention of the last maybe 55 minutes or so, and hand it back to, actually not hand it back. I'll take a deep breath, take a little mental break here, and would like to call on Stephen Solis from ERCOT to come onto the stage and share some of his thoughts and activities at ERCOT to consider the adoption of 2800.
Thank you for that, Jens. My name is Stephen Solis. I'm a Principal System Operations Improvement with ERCOT. Many of you are probably aware that we did have a large event in May of 2021, otherwise known as the Odessa event. And while we've had other smaller inverter-based resource issues, that particular event really got our attention, got NERC's attention as well. There's a report out on the NERC website. Since that time, we've been monitoring, and we're seeing other events, smaller events on the system, primarily ride-through issues, but other oscillatory, other different issues are showing up. And so we saw the need to really create a task force in our region. So in January of this year, we created the Inverter-Based Resource Task Force. And one of the key things that we're trying to do is essentially prevent the same or similar type events from occurring on the ERCOT system. And on the ERCOT system, we have quite a bit of inverter-based resources that have integrated to the system and are looking to continue to integrate in our system towards, in the future, them being really the predominant technology that would be integrated. And so when we looked at the timing of 2800 and we saw that it was pretty close, we saw it was a good opportunity for us to try to leverage some of those particular technical aspects of that standard into our grid code here in the ERCOT region. So when we looked at that, we wanted to really understand how we aligned with it within our current rules, so that we can make a good decision on whether we go wholesale adoption, we do a piecemeal adoption where we cherry pick, as Jens mentioned, certain parts, or look at how we could change the wording essentially to meet perhaps a piecemeal adoption, but in ERCOT language, where we use our definitions, where we use our functional entities that we've identified within our region. And so we've been working with EPRI to perform a gap analysis. The high-level gap analysis is really just comparing topic to topic. Do we have ERCOT rules that match 2800? Are we missing? Do we, in some instances, perhaps go above and beyond what 2800 says? And then bring that type of analysis to the stakeholder group for the Inverter-Based Resource Task Force to get their feedback. With the increasing level of penetration of inverter-based resources that we are forecasting in the next 2 to 3 years, we really see some urgency to trying to get at least part, if not all, of 2800 adopted into our ERCOT regional rules. So whether we do wholesale or prioritize, we're going to try to get a first wave done within 2022, and then take if we end up going piecemeal, then have like the medium priority items that we do in 2023, and then the lower priority in 2024 based on the feedback that we get from the task force. We're really trying to do this so that we don't have to get into some type of moratorium or something like that where we can't let inverter-based resources come onto the grid until we get these issues resolved. But technically, a lot of these resources are capable of meeting some of these requirements. But then, as Jen's mentioned, capability, and then we also have to work on which specific capabilities we want to enforce, make sure that they're put in service, make sure that they're tuned to perform the way we expect. For those of you who may not be familiar with the ERCOT rules, we have the nodal protocols, which are kind of our overarching high-level rules. They tend to be a little bit broader in scope. We have the nodal operating guides, which dive down a little bit into more detail to perhaps operators and other entities like that to get more granular detail about what needs to be done. We also have the planning guides, which guide our planning processes for studies, interconnection studies, reactive studies, those types of things, especially as entities are seeking to integrate into the ERCOT system. And then we also have a model quality guide that guides the specifics on the models, whether it's our positive sequence EMT models, which we use PSCAD here in ERCOT, to make sure that we get the essential aspects to be able to model and study the system appropriately. Our protocols, guides, other binding documents that we have within our ERCOT region, they're really focused to harmonize. They should not conflict. And we also have NERC reliability standards that we want to make sure our ERCOT rules are harmonized with. We can perhaps specify how we meet a NERC standard, which entities are responsible for meeting those things, and perhaps even going a little bit further into detail. When we do that, we would take a similar approach with 2800 to make sure we know who, we know how, and we identify in all the appropriate places in our rules. So it is quite a big task, but as mentioned, we see this as being a potential technical standard that we can leverage and help us solve a lot of the issues that we're seeing on the ERCOT system today with inverter-based resources. I do want to mention there are specific ancillary services as well within ERCOT, reserves, voltage support services, frequency support services, where perhaps there are requirements that apply only to a subset of participants that engage in those ancillary services. To show you an example of the high-level gap assessment here, comparing our nodal protocols to the IEEE 2800 standard, you can see there's several opportunities that we have here in the ERCOT region to enhance our grid code to make sure that the capabilities are there for the inverters that are integrating into our system. So we have a tall task ahead of us, but we're now diving into the more detailed gap assessment where we're looking more into the details, perhaps even coming up with language that we can present as solutions to integrate into our ERCOT protocols, operating guides, planning guides, modeling guides, to make sure that we either align with 2800 or we're referencing 2800 on how to perform as necessary for all the variety of different reliability performance metrics that are identified within IEEE 2800. That's where we're going. If I can broadcast the signal for any developers, we are moving in this direction. So it would be good for developers to take this to heart, make sure you're talking with your vendors, your OEMs, making sure that they're ready for this, that they are going to be able to be compliant with their equipment, being able to have the capability to perform to IEEE 2800 requirements. So with that, I'll pass it back on to Rudy so he can take over the rest of the presentation.
Okay, thanks, Stephen. And also thanks to Jens for his presentation. Before we get into the Q&A, just a couple of quick things. We mentioned earlier that there are some other webinars that are one taking place tomorrow and one taking place at a future date. So please keep those in mind. I know there were quite a few questions that came in regarding getting copies of the slides, and there is a resource tab on the web or the webinar platform, and so you can actually get the slides from there. And there's also links on that resource page to other information that might be important as well. So with that, I'd like to get to the Q&A, and those as Jens and others, you can feel free to turn on your videos and microphones at this point. There are quite a few questions. I know that Manish has been flagging a few questions for the panel. I don't know if we want to start with those perhaps, and then I know we're not going to get to all of them because there probably are about 30 or 40 good technical questions in there. But maybe we could start out with those questions that Manish flagged within the team here. Jens, how do you want to approach that?
Yeah, let me take that first question. And I already saw a few questions that I need to rely on Manish and maybe others here to get answered. But yeah, thank you so much, everyone, for hanging on here for more than an hour. I know this was quite a bit of information, and yet we still have more than 750 folks on the line, whether or not you're listening is a different question. But you did submit questions, so let's tackle the first one. That was, how will this interact with IEEE 1547? And my answer to this is based on a citation from clause 1.4, the first paragraph in the standard. There reads that for radial subtransmission systems, the standard intentionally overlaps with potential application for IEEE 1547, in which case it remains at the discretion of the authority governing the interconnection requirements to decide which standard is applicable. So it's important to understand that 2800 was really written with networked or meshed subtransmission and transmission systems in mind, whereas 1547 was more so written for radial distribution and radial subtransmission systems in mind. And for the radial subtransmission, that's really where you have this intentional overlap, and it ultimately depends on what the grid planner, including the grid protection folks, would decide makes more sense. So if you need, for example, negative sequence current injection from these resources on your radial subtransmission system for some reason, then you may rather want to go with 2800. If you don't need that and you more care about unintentional islanding detection and clearing, then you may want to go with IEEE 1547. So those are decisions that each jurisdiction would have to make based on their own analysis. Hopefully that answers the question. Shall we take the second question here that Manish elevated, and that is whether we think that IEEE 2800 will be part of the UL 7041 certification in the future. Now, we can certainly not talk for UL. So again, I'm going to cite from the standard, and footnote 152. Yes, we love footnotes. Footnote 152 reads, development of dedicated type test procedures complementing the standard is recommended. Existing type test procedures, such as IEEE 1547.1, IEC 61400-21, FGW TR3, FGW TR4, FGW TR8, IEC 62927, IEEE 115, IEC 634-4, or IEC 634-5 16 may or may not be appropriate to verify compliance with this standard. Certification of equipment, for example, under UL 7041 SA or SB, or the UL 7041 CRD for power control systems, is outside the scope of this standard. So what that means is that type testing can play a role in the conformance framework of 2800. As a matter of fact, 2800 requires some form of type testing to verify IBR units have some capability, but also, and probably even more so, to generate measurement results that can be used to validate inverter-based unit performance, which would then feed into the the IBR plant design evaluation to understand how the components and the design together will make the plant compliant with the 2800 requirements at the reference point, which is either the POM or, as applicable, the POC. And therefore, it is not clear at this point whether UL would specify a dedicated certification standard for inverters for 2800 compliance. As a matter of fact, it might be less relevant and less needed for these large plants, because those are always case-by-case design plans, whereas the UL certification is traditionally focused on consumer equipment, which relates more to the smaller scale inverters used at under 1547. So that's kind of a long answer to say we don't really know. Manish, the next one is for you. You want to take the
By the
one
way, yeah, there's a little bit of background noise, so I don't know if whoever's, let's just have whoever's speaking keep their mic on.
So Jens, in respect of time, I think we could prioritize here and talk a little bit about the differences between 519, IEEE 519, 1547, and 2800. If you can help summarize, harmonic limits, if they're different and why from 519 and 1547.
Yeah, thank you, Manish. And thank you, whoever asked that question. Certainly there's a lot of interest around IEEE 2800 harmonic current and voltage limit requirements. So you may remember that 2800 does not specify harmonic voltage limits. It recommends to the transmission planner to specify those. Now, how can they specify them? It would certainly require some more sophisticated modeling, including a representation of the inverter-based resource in the frequency domain, and to a certain extent, maybe the time domain. The concept of 2800 is that it specifies, so let me also preface this with the statement that there is no conflict between 2800 and IEEE 519. We actually work very closely with the leadership team of IEEE 519, and they recognize that the current harmonic limits in 519 are not applicable for voltage source converter resources. They were written more in the spirit of thyristor-controlled switched loads from the past. And the agreement is that for transmission-connected resources, IEEE 2800/2022 now specifies the expectations around harmonic voltage limits for wind, solar, and storage plants connecting to the transmission grid. That said, though, that if the transmission planner does conduct studies and does specify voltage harmonic limits at the connection point, which may or may not coincide with the voltage harmonic limits specified in IEEE 519, and the developer is able to show that they are meeting these transmission planner specified voltage harmonic limits under 2800, then the transmission planner may waive the harmonic current limits that are specified in the standard, because ultimately what counts is not the current limitation, but the voltage limitations at the connection point and near customer points. Now, the complication about these voltage harmonics is that whenever anything changes in the grid, whether that is the connection of a new customer or whether a load customer or whether it's a connection of a new inverter-based resource, then that might impact the voltage harmonics at that existing IBR's connection point, and therefore potentially require additional mitigation measures by existing plants. And then it really becomes more a question for the lawyers and process folks to what extent you can hold responsible existing plans for an issue that has been caused by a newly connecting plant. The spirit of 2800 also with regard to the post-commissioning performance monitoring, which may include harmonic voltage monitoring, is really to create a set of expectations and collaborative working framework so that different parties can more effectively and more efficiently work together to meet requirements that ultimately uphold bulk power system reliability and bulk power system power quality. So in a nutshell, there is no conflict. The framework is aligned and had been agreed upon with IEEE 519 leadership, and IEEE 519, as it is being revised these years, is also considering this agreement in its latest version. Thank you for that question. Okay, so then, Manish, let's maybe take the last question about whether the grid relies on fundamental frequency being established by rotating machines as one of the last questions here before we adjourn. That seems to hint at a question to what extent IEEE 2800 may be sufficiently specifying requirements for power systems with very high, if not even 100% IBR penetration. And the answer is that this first version of 2800 does not sufficiently specify performance requirements for 100% inverter-based penetration. So to some respect, the standard did still consider that the power system the plants connect to under 2800 2022 would connect to a system where there are certain amounts of rotating machines, whether you call them must-run, it's with synchronous generators or similar. Now, we do not know yet whether possibly the minimum requirements of 2800 could in many cases be, or in some cases be sufficient to operate a system with 100% penetration. You saw the example simulations for the ramp rate and fast frequency response discussion today, which did indicate that with 2800 requirements, you may be able to operate a system at 100% IBR penetration, at least from the frequency and stability viewpoint. But the judgment is still out and probably will be out for the next couple of years to identify cases where the IEEE 2800 requirements would fall short for 100% penetration systems. And therefore, whenever a standard is published, the work to revise that standard just is about to start again. We'll wait a little longer until 2800.2 has commenced and has been completed, because it tends to be the same people write these standards. There's all expectation that 2800 will be revised in a couple of years again to consider learnings, including those about 100% IVR systems. And maybe, Rudy, that's a good concluding word to hand it back to you to close off the seminar.
All right. All right. Thank you very much, Jens. And thank you to all those many people who are behind the scenes putting this presentation together, and all the work that's gone on 2800 the last few years as well. With that, and our thanks to the speakers, we also wanted to thank the audience. This was a very well-attended webinar. As I mentioned before, you can actually download the slides from the resource tab, and we should have some other information on the website about the content. You can always go back to where you registered, but we'll be looking to put some of this content up in an appropriate place as well in the near future. So thank you again to everyone, and we look forward to joining another webinar in the future. Thank you and have a good day.
Thank you so much.